In this video, we're going to introduce the idea of a Markov chain. So this is going to combine our knowledge of probability as well as matrices into an applicable mathematical model called Markov chains. These were named after Russian mathematician Andrei Markov. So these systems have a finite number of states, okay, so some number of options, and the system evolves from one state to another. So at any particular stage of the process, you're in one of the n states, okay, so one of the states is occurring. So some sort of basic examples might be the stock market. So in a really low-level way, each day, per se, if we think about when the stock market closes, okay, a stock will increase from the day before, decrease, or stay the same. Okay, so here we would have three states that happen, and each day one of them has to happen. Okay, and then you can talk about the likelihood that if you increased yesterday, that you're going to increase again the next day. Commuting is one, so maybe if you're going to school or work, okay, or work, maybe we're not commuting so much right now, but you might be, okay, so you could drive, okay, maybe sometimes you take the bus, maybe sometimes you bike, maybe sometimes you walk, okay, maybe you carpool sometimes, okay, there's lots of different ways, so it depends on who you're talking about. So here, maybe you have 5 states, okay, but each day you do one of these things. So when a system evolves from one state to another by way of chance, so in terms of probability, we call the system a stochastic process. Okay, so this is sort of the broad term, and we're going to be studying one type of stochastic process. So this is called a Markov chain. So if you have a stochastic process where the likelihood, okay, that you move from one state to another does not change. Okay, so it's constant throughout. So the examples I gave maybe are not good examples because the way the stock market changes depends on a variety of factors. So knowing that it increased probably isn't enough information to know what it's going to do the next day. Okay, so it depends what's going on in the world, etc., etc. But we can use these as simplified versions to approximate or model what could happen using a Markov chain. Okay, so that's what Markov chains are used for often. Okay, so to model or predict behavior of various types of systems. So they're used all over the place. So I just listed a few. Okay, finance, market research, genetics, medicine, demographics, psychology, political science. Okay, any type of system where you move in between different options. But let's talk about this using an example. And this is a sort of a basic example. So each day, Shane thinks about having dinner. Okay, he's going to decide whether to go out to a restaurant or eat at home. Okay, so those are his two options. And he always makes his decision depending on what he chose the day before. Okay, so what happens the day before is how he chooses the next day. So if he ate at a restaurant one night, there's a 5% chance that he eats at a restaurant again the next night. If he eats at home one night, then there's a 20% chance he goes to a restaurant the next night. Okay, so this is a Markov chain, so to answer the question, okay, it is a Markov chain. It's going to have 2 states. So he either eats at home, okay, or he eats at a restaurant. Because I'm going to be referring to these, I'm going to call this one H and this one's R. Okay, so the probabilities that he goes from one to the other, at each step in the process, is the same. Because he always picks depending on what he did the day before. So each day, the chance he switches is the same. So that's what makes it a Markov chain. So we can represent this graphically using what we call a transition diagram. Okay, so what you do is you draw the states. Okay, so I have an H and an R. and then you draw the chances that he goes from one to the other. Okay, so up here it said there is if he eats at a restaurant, there's a 5% chance he goes to a restaurant again. So that's restaurant to restaurant is going to be 0.05, so 5%, so the probability is 0.05. If he eats at home, there's a 20% chance that he goes to a restaurant the next night. Okay, so then there's a couple of things we can infer from those two statements. So if he eats at a restaurant one night, there's a 5% chance he eats at a restaurant the next night. That means there has to be a 95% chance that he eats at a home the next night. Okay, if there's only 5% that he goes to a restaurant, there's 95% that he goes eats at home. Similarly, 20% he goes from home to restaurant means that there's 80% chance that if he eats at home one night, that he eats at home again the next night. Okay, so this is what our transition diagram would look like for this Markov chain. Now, one way that we often like to use is a transition matrix. Okay, so like I said, this chapter is going to combine probability with matrices. So the transition matrix, often we call P for some reason. Okay, it's going to be a 2x2 matrix for this example. Okay, so why is it 2? So both of these are 2 because they're the number of states in our Markov chain. So because we have 2 states, that's why it's 2x2. And then what we do is we label the rows with the states and also the columns with the states. Okay, so what's going on is the rows represent our current state. Okay, and the columns represent the next state. So, let's get a different color here. So if we're inside, the probability here, we're going to put in probabilities in this matrix. So in this spot, the row 1, column 1, it's H to H. So this means that he eats at home one night and then he eats at home the next night. So it's the probability of going from H to H. So in row 1, column 2, it's going to be the probability he goes from H to R. Okay, so similarly down here, it's the probability of R to H, and then the probability of R to R. So for our example, okay, this is going to be 0.8 and 0.2 and 0.95 and 0.05. Okay, so those are just the probabilities that I just took from the transition diagram or from the question. So some notes about the transition matrix. Okay, so these are what I just said. The rows of the transition matrix are labeled by the current state, so the state that you're currently in. Okay, the columns are labeled by the next state. So the one that you want to go to after one stage of the process. Okay, now one thing that's important, okay, and I did in my example, is the rows and columns need to be labeled in the same order. Okay, so I did H and then R, so that means up here I had to do H and then R. So it doesn't matter what order you pick, but once you pick one, you have to use the same one. Okay, the transition matrix will always be a square matrix. Okay, in fact, it's going to be n by n, where n is the number of states. Okay, because we're indexing them with the states, so indexing the rows and columns, so there has to be the right number of rows and columns. So Pij, so if you don't remember, okay, what this stands for in matrix world is the entry in row I, column J of our matrix P. Okay, so this entry is going to be the probability that you go from state I to state J. Okay, so whatever state you labeled on row I to the whatever state you labeled in column J. Okay, now this is in one step. of the process. Now, the entries in each row, so if we look up here, if we look at row 1, these entries sum to 1. If we look at row 2, these entries also sum to 1. In fact, the entries will always sum to 1. Because if you're currently in state H, you have to go to either state H or state R. Those are your only options. So the probabilities there should add to 1. Okay, so that's some properties for the transition matrix. Okay, now suppose we have some extra information. So the process has to start somewhere. So let's say that we know at the beginning, so today, there's a 75% chance that Shane's going to eat at a restaurant, okay, tonight. So this is the beginning of our process. So we're going to put this into a matrix that we call the initial state distribution matrix. Okay, so it's the start of the process. So once we start the process, sort of the transition matrix is going to tell us how to move from there, but we need to know how it starts initially. So the initial state distribution matrix, or the initial state matrix, is always a row matrix. Okay, so it's going to be 1 by n, where again n is the number of states. We're going to call it S0, okay, and the ith entry is going to be the probability that we have state I at the beginning of the process. Oops. Okay, so in our example, okay, S0 is a 1 by 2 matrix, because we have 2 states here. And then we're going to label in the same order. Okay, we're always stuck with the same order. So once I picked H and then R, I use that forever. So then in this entry here, this is the probability of R today. Okay, so and this one would be the probability of H today. So to find that, we want to use this special information that we got. So there's a 75% chance he's going to eat at a restaurant tonight. So that means that this probability has to be 75. So if there's 75% chance he eats at a restaurant, there's going to be a 25% chance that he eats at home, if those are his only 2 options. So that's S0. I guess I'll talk about that later. So what if I want the probability that Shane eats at a restaurant tomorrow night or the night after? Well, I could use the ideas from chapter 2 and maybe use a tree diagram. Okay, so this one would be tonight. I'm going to call it H0 and R0. Okay, so he either eats at home or at a restaurant. And we know these probabilities. Okay, now after today, he follows the transition diagram. So he could go eat at home again, or he could go to a restaurant the next night. So those are his options. Now, if he ate at home this night, we know the probabilities that what he does the next day. So they have to be 80% chance he eats at home again, 20% chance he eats at a restaurant. If he ate at a restaurant, these probabilities are different. So there's a 95% chance he eats at home, and there's a 5% chance that he eats at a restaurant again. Okay, so that would be tomorrow. Okay, so then the probability that he eats at a restaurant tomorrow is actually the probability of R1. Okay, so this is going to be 0.25 times 0.2 plus 0.75 times 0.05. Okay, so if you compute that, you get 0.0875. Okay, now if you wanted the next night, you'd have to make this tree even bigger. So you'd have to go home 2, okay, restaurant 2. So you're getting a bigger and bigger tree diagram, which makes this not ideal. Okay, now the probabilities depend on what he did the day before. So if he ate at home, then I know it's 80-20, but if he ate at a restaurant, it's 95 and 5. Okay, so if he wanted the probability he eats at a restaurant the next night, you're going to have to add, maybe I'll just do this with a highlighter. You're going to have to add all these paths that end with R2. So there's going to be 4 different ways that he could end at a restaurant. Okay, so obviously we can compute that, but we might not want to do it this way, because if I go further into the future, I'm going to have a massive tree diagram. And if I want to predict the future, okay, that's almost, it's impossible to generalize this tree diagram situation. Okay, so you'd want to multiply along those paths and then add them up. So what we're going to do is use matrices instead. So we're going to define a case state matrix. So like the initial state matrix, but we're going to call this one SK. And it is the state distribution matrix, but after K stages. Okay, so after K steps. So that's why we call S0 S0, because it's after 0 steps. It's the beginning. Okay, so K is going to be a 1 by n row matrix again. The ith entry is going to be the probability that you're in state I after K stages. And just like in S0, we're going to have the entries summing to 1. Okay, so S1, so this is tomorrow, for our example, okay, this is going to be the probability that eats at home tomorrow, and the probability he eats at a restaurant tomorrow, because we want to keep our states in the same order. So because we already figured out our probability of R1, we said was 0.0875, I think, 75. We know the probability it's at home is going to be 0.9125. Okay, now we can actually compute this using a matrix operation. So what this is going to be equal to, I'm just going to tell you and then we can check. Okay, this is S0 times our transition matrix P. Okay, so it's going to be our initial state, which was 0.25, 0.75, times our transition matrix, so 2.95, 0.05. So if we do this multiplication, let me just check that we can. So this is a 1 by 2, and this is a 2 by 2. Okay, so the 2's match. So we can do the multiplication, and we're going to get a 1 by 2. Okay. And then the entries, so we do this row times this column. Okay, that's going to give us our first entry. And then we're going to do the same row with the other column to get our next entry. Okay, so if we do that, we have 0.25 times 0.8 plus 0.75 times 0.95 for our first entry. And look what happens in our green entry here. We have 0.25 times 0.2 plus 0.75 times 0.05. Okay, that's exactly what we had before. I'm going to make that a bit bigger. So if we compute this, we're going to get 0.9125 and 0.0875. Okay, and it's actually going to happen, so notice again, these sum to 1. Okay, that's a good check to do to make sure you didn't make a mistake. Okay, now you're going to be able, so this one, S2, is going to be the day after. To find S2, what you're going to do is again multiply by P, but this time you're going to take S1. Okay, so you're going to take our what happened yesterday, the probability that we were in each category, and we're going to multiply it by P. So multiplying by the transition matrix always just moves you one step in the future. Okay, so if you do this multiplication, you're going to get 0.813 and 0.187. Okay, so this is the probability of H2, and this one would be the probability of R2. Now, if you did compute it before with the tree diagram, okay, you should have got this number. It should be the exact same. So, some notes about these. For each K, the sum of the entries in SK is equal to 1. Okay, every time here you have a row, you're going to sum to 1. Each column of your SK should be labeled with a state. Okay, and the columns should be labeled in the same order as whatever you chose for your transition matrix. Okay, now the ith entry here is the probability that you're in state I after K steps or stages of your process. Okay, so this is after so many steps. Now, hopefully I've convinced you that when we multiply by P, we move a step in the future. So we can compute SK, the distribution after K steps, by taking the distribution after K minus 1 steps and moving it forward 1 by timesing by P. Okay, so hopefully you believe this. This is what we're going to use to compute these distribution matrices. Okay, so this is an important formula to compute. And it seems the tree diagrams are nice, but because the trees get big so fast, it's actually going to be better to use this matrix multiplication. Okay, now we can actually rewrite this a bit differently. So instead of determining this SK recursive, we call this recursively, because in order to get SK, you take S0 and you'd have to compute S1. And then you'd take S1 and you'd compute S2 using S1. Okay, and then eventually you get to SK minus 1 and you compute SK by multiplying by P. So you have to compute every single one in between 0 and K. We can also use powers of the transition matrix. So let's just see. So S1 is S0 times P, and S2 is S1 times P. Okay, but we know that S1 is actually S0 times P. So I can replace it with that, and then P times P is P squared. Okay, so I get S2 is actually S0 times P squared. If I do S3, it's going to be S2 times P, and I know that S2 is actually that, so I can replace it. So it's S0 times P squared times P, and P squared times P is P cubed. Okay, so maybe you see the sort of pattern here. So when it's 1, it's to the power 1. When it's 2, it's S0 to the power 2, or S times P to the power 2. When it's S3, it's S0 times P to the power 3. Same thing's going to work for SK. So you can continue this. So if you prefer, if P is a transition matrix and you have initial state matrix S0, you can also compute the K state matrix, so SK, by doing S0 times P to the power K. Okay, now I don't, so you can skip sometimes, you don't have to compute all the S's, you can skip straight to SK. Okay, but just note here you're computing powers of a matrix. Okay, this is not fun. Okay, but what this can be useful is that you can skip some powers. Okay, so suppose you wanted S8. Okay, that's going to be S0 times P to the 8. Okay, so we actually could compute SP2, so P squared is P times P, and then we could compute P to the 4, which is p squared times p squared. So notice that we didn't have to do p cubed. Okay, we jumped straight to p to the 4. And then we can jump straight to p to the 8, by doing p to the 4 times p to the 4, because you add the exponents, right? The exponent rules work the same for matrices. So you can sort of skip ahead some, okay, but powers of matrix are not fun. So in general, I tend to use the first method more often, unless I have to go really far into the future. So some nice facts about p to the k. Each row, again, sums to 1. Okay, and Pij, remember this is the entry in the ith row, jth column of p to the power k. What this is the probability that you go from state I to state j after k steps. Okay, so that's kind of neat that it has the same property as a transition matrix, except with this after k steps condition. Okay, so you're not just doing one step like p is, you're doing after k steps. So that's a brief introduction into Markov chains.